probably could, because I was taking summer classes last night.
Alright, so let's continue and oxide part instead about 12 or something, and we will have our presentation for our third. So now we are going to study the reaction of those oxides, which are pretty much depend on the condition. Okay? The mechanism under the basic condition. Under the basic condition, let's use one example for the overall reaction. You are going to use the sodium azide. Sodium is Na plus. Azide is 3 nitrogen and carry like 1 negative charge. So this part is negative, this part is plus, this part is negative. Now, this nucleophile reacting with our epoxide, and our epoxide is this. So that will be our epoxide. And plus water, so if I specify the condition, and I said your pH 9.5, higher than 7, so therefore the solution is basic. Okay? So you keep the solution basic, you are not protonate too much of the azide ion. So that azide ion will attack our epoxide ring. And we have the N3. Attach on the carbon, and then so I don't have to draw the H or something. Okay. I try to draw the OH. Your OH, so almost on the other side, but your OH will be on this side. Right, and plus NaOH. Right, now let's see the mechanism. So first step, you will take this azide is basically see what part is plus and what part is negative. It's a very good nucleophile, right? And you have the epoxide. Now this will attack on this side, which is less hindrance, and produce N3 on that. Now this time we know where will be your oxide. So I draw all the electrons. At the beginning, you also have like 2 pair here. Let's draw that out. That makes sense? And now you will see where the sodium hydroxide comes from, right? So next step, so this will be our alkoxide. The alkoxide rapidly abstracts a proton from the solvent. Our solvent is H2O. So again, this will be our very strong base. And if you have some water that's nearby, I think you get those kind of basic electron flow mechanism. You have the arrows, the electron always go from the double bond or long pairs. So that finish our reaction. Plus the OH. OH one negative. So the first step, is SN2 reaction. Okay, step 1, your SN2 reaction. Even though your leaving group are not really totally left, right? In the usual SN2 reaction, your leaving group are like a water or a toast base, or here are just totally like pop out. But in this SN2, so the leaving group are just break a bond, and so that open the epoxide ring. Then you remember, if you have an SN2 reaction, the configuration or inverse. In R1 you study, if you start with the R configuration, if you go through a SN2, you will end up only a S configuration. Okay? If you go through a SN1, you will have a reciprocal mixture. Now, what do we mean by the inversion of the configuration? Okay? Let's start with a chair conformation of cyclohexane epoxide. So like that. And here is our ring like that. Okay, I think I miscounted the carbon. It's not a cyclohexane, it's a cyclopentane. But anyhow, you have this configuration here. Okay? Well, when you have SN2 reaction, as in the SN2 reaction, in this example is NaO. So the sodium isoxide, even like the ethanol, okay? And what you produce is like this. So this isoxide and come attack from the top. And here we produce this alcohol like that. Right? It's kind of the inversion of your configuration here on this carbon. So right now this carbon has O from the below. After the attack, you have that O on the top. So that's, in that sense, it's an inversion of your configuration. And now here is the important rule you want to memorize. Okay? So the anion nucleophile attack the epoxide from the less hindered carbon. Let's see some of those examples. We have some of the hindered and less hindered. Okay, so one example is if you have this epoxide here, right? So in this epoxide, we have two carbon. The left side is less substituted, so therefore it's less steric hindrance. If you take a sodium methoxide, NaO6,3, and in the methanol, C3OH, okay? And what you see, you produce your OH is on the side, epoxide. Then here you will have your mesoxide.
Chemical peroxide?
Huh?
What did you say before?
We have this epoxide. We have this epoxide, which is asymmetrical, not symmetrical. Here you have two methyl and one methyl. Right? So if you have those kind of nucleophile, which is anion, even though you don't see the anion clearly, you know this Na is plus and this is negative. Right? So Na is not the one that in the chemical reaction. Na is just the suspected ion. Got it? So the really nucleophile here, nucleophile is this mesoxide. This mesoxide is our anion. So therefore, in this case, you have a choice. You either like make this mesoxide attach on this carbon or this carbon. So that just then you have to memorize, and your mesoxide will attach on this carbon, which is less hindrance, has less methyl. And you have to break this ring. After you put this mesoxide here, so this ring will break. Not a whole break. You break this bond, and then you still have this O here, and then O will getting a H from the solvent. Right. Any other questions? Right. So if I give you this product, let me make this product very easy to read. So this product is you have this phenol. And OH here, right? So it looks like you have alcohol, a secondary alcohol. So you have one carbon here, another carbon here. So you primarily see you have 3 carbon beside this benzene. And in this chapter, you talk about you can use the epoxide to make those kind of alcohol. What it did here. So you can think about that one can come from your anion nucleophile. There are many different anion nucleophile. You can use Grignard. You can use organolithium. So this is one of our reactants. So then other reactants, it will be this epoxide. This epoxide. All right. Any questions? Let's see, this epoxide is 1,2-epoxy propane. So this guy, the 1,2-epoxy propane, and you have 2 carbon, 1 carbon here, only have 2H and then this O. The other carbon has methyl. So that carbon is a little more crowded. So then this will be the anion nucleophile. You take the MGBR away. So this here has relatively negative charge attack on this side. And that's why we produce that. Right? Any questions?
You guys start beeping? Yeah. I've been hearing that really, I don't know.
It's an alarm.
then we have this epoxy ring on the first and the second carbon. So even though this looks like lengthy, but what is the important point is this epoxy ring here is not symmetrical. Right? So you have one carbon that has less substituting, less hindered. And if you use those guys, you know those guys will give you, so this pretty much is the same as hydride. Right? A hydride is a very strong base. Right? So therefore your condition should be basic. If you have any source of those protons, then this H negative going to grab the proton and produce H2 gas. So under that condition, and you will change this epoxide into this 2 decanol. Not the 1 decanol. You get this 2 decanol. That's it, because let me erase those. Because your H1 negative, okay, this H1 negative come from the Al lead. So this actually, if you write this clearly, you will write the negative not on H, you will write H on the aluminum. Okay. But you will take these 2 electrons in the bond between H and Al and attack that carbon. So intermediate, so out of this reaction, these 2 together will give you the intermediate. And then intermediate you already saw many times with your alkoxide, which means you have the oxygen bound to O, then the oxygen has negative charge. So that's alkoxide you produce from the reaction of this 1,2 epoxy decane with lithium aluminum hydride. Okay, now let's do a few more practice. This problem 16.13. What is the principal organic product formed in the reaction of ethylene oxide with each of the following? So I think this problem is relatively easy. Give you the ethylene oxide. I saw like some of you have a little difficulty on the exam to remove the name. Sometimes I will give you only the name, and you have to figure out what is the structure for your reactant. So this is the ethylene oxide, which is symmetrical, right? So if it's symmetrical, then you don't have the problem like what side to attack, but you still want to memorize what will be your nucleophile and what is your product. So the first reaction is sodium cyanide. Sodium cyanide give you as NaCN. And this one will actually give you the Na plus. Na plus really not that important like ions. So you will have like this. So this will be a cyanide. Then cyanide will be really the nucleophile that will attack your epoxy side. Okay? So you will just see this, you can write in opposite way, you will write NC and that. Then you plus your epoxide. And then this electron attack on this, then your ring break. So you produce C and then C and C and O like that. From here, if you write a C, you will write all the H. Then as a step, you have water or you have ethanol. So this alkoxide take the H away from the methanol or ethanol or water and produce the final product. Now you can write into a structure like that. Okay, so the problem number 2, you will use sodium azide. Okay? Azide, as we saw before, is 3N double bond to each other, and then the 2 at the end, and has 2 lone pairs. So negative charge on the end, positive charge in the middle. That's a very good nucleophile. Similar, so if you take this reaction with your epoxide, now our reaction, I will simply use N3 for simplicity for our azide. So N3, bond to 1 carbon, you have 2 carbon, in the ethylene oxide, so you have 2 carbon, and then you have this alcohol like this. Okay, so I think that no matter what kind of nucleophile you have, maybe those anion nucleophile in basic condition or some of those neutral nucleophile in acidic solutions, and I think you will see the pattern is your nucleophile and your OH forming on different carbon. So that's the result of this epoxide with nucleophiles, with the result of opening the ring. Right? So we have 2 carbon here from the epoxide. Our nucleophile are 1 carbon, and our alcohol, the OH, on the other carbon. They are not on the same carbon. Right, so C is you use sodium hydroxide in water, and that is hydrolysis that will simply open the ring, give you a diode. Right? So you have OH or HO, so this is our hydroxide. Okay, so D is phenol lithium. Phenol lithium plus the ethylene oxide epoxide. It's a very good way to produce alcohol with 2 more carbon from use green yard or organolithium. Okay, the last one is this kind of ion. We call that acetylenic anion. Acetylene is the simplest triple bond compound, right? So if you have a terminal alkyne, and you will have a negative charge on 1 carbon, and this kind of anion, we say is acetylenic. So we'll take that, and this you can write alcohol like this. So let's use those line structures. So this is a negative charge here, and 1 more carbon, so we have 4 carbon. Plus our ethylene oxide. So keep tracking the number of carbon. Right? And now you will have all together, if you put these 2 together, you will get a 6 carbon. I see that makes sense. So we have this part here. The name here is called the 3. Take a sign and 1 or. Now let me use dot to see where are all those carbons. So you have carbon 1 here, carbon 2 here, carbon 3 here, carbon 4 here, 5 here, and 6 here. So that's the 6 carbon. Okay. Now 4 of the carbon come from the acetylenic anion. 2 other carbon from this epoxide. All right, any questions or comments? All right, now if you have those acid catalyzed ring, meaning the nuclear physical attack occurs at the most substituted carbon. When the epoxide oxygen is protonated with acid. Okay. So the transition state for the reaction of methanol with conjugate acid of 2,3-epoxy 2-methylbutane looks like this. Okay. So you use the protonated epoxide, and if we have epoxide, we see this, see the structure. Okay. So here will be your 1 carbon, and the other one here will be the back one, and here 1 more carbon, and here another wedge. So initially you have epoxide, right? And epoxide, that is this H. Okay. Epoxide, let's see, you have 1 O here. So this makes this asymmetrical. So this O here, and let's see, before we open the ring, I will just use 2 solid lines, so these are our initial epoxide. Okay. Now what we do in the acid catalyzed ring opening, you first will put a proton here. So you attach a proton here. Okay? If you attach a proton here, so this guy becomes relatively positive. Now the ring will begin to open. Okay? Now, as we said here, as this paragraph, the ring, this is step with SN2. SN2 is supposed to the bond breaking here, and then your bond forming at the same time. Okay? Now let me draw that coming in like a nucleophile. Our coming in nucleophile is this messenger. So nucleophile has the electron on it. Okay? Now this nucleophile is ready to attack this carbon. Okay? So this carbon has more substitution on it. You have two metals. And this carbon has only one metal, one H. If you use those green yard or organolithium in basic condition, it will come on this side. Now if you use this messenger with some of those acids, it will come on this side. The reason is like this. So before the nuclear fire attack, you first will put a proton on this oxygen. Make this oxygen relatively positive. I mean positive now. Okay? Now this study the mechanism we find out. So this bond breaking here, the bond forming there, liberal different state, different speed. So this bond will break first. Break a little more first. Before it totally break, then the nuclear fire will come in and attack. So now if I change this solid line into a dash, that means this is going to begin to break. And let me even use a different line. Let me use change my pen. So now we will have this bond ready to break. Okay? Partially break. So what happens if this bond partially break? Oxygen obviously has a positive charge. It will grab the electron away from this bond. Make this carbon carbon cation light. Right? So even though in the SN2 reaction, you don't produce the carbon cation like intermediate. But in this transition state, you have some of the characteristic of carbon cation. Right? So then remember, if you have a carbon cation, you always have a choice. If you produce a carbon cation here, and here is a tertiary. So here, this carbon here, have a little tertiary carbon cation. If you have a carbon cation, it's tertiary, it's more stable than here, secondary. That's the main reason electronically. When you have a acid catalyzed ring opening for the epoxide, and your nucleophile will attack on the more substituted or more crowded side. Now your electron come in from the oxygen, from the messenger, and attack the carbon cation. So when this is finished, and your bond between that carbon O will totally break, and you will have this OH here, and you will have that then other methyl, and you have this C3. Now this one becomes positively charged. So you did not really get your final result yet. You have somehow deep protonate. Then very easy, you take some of those other like methanol or water, that will take the H plus away, and you produce your final result. Right? So let's say another methanol come in and take the H away, then this will become our final product. The final product summarize the two different ways of opening the epoxide ring. Right, so this is simple epoxide. So this is less hindrance, and here is more hindrance. But when you have those acid catalyzed ring opening, your nucleophile will attack on this part. In those basic conditions, basic solutions, which means you will have a lot of those anion nucleophile, and your attack of the nucleophile will be from this less hindrance or less substituted carbon of the epoxide. Right? So if I give you these two reactants, and probably sometimes even like more clear, I will use some of those acids. I tell you, will use this H2SO4 catalyst. So you predict what will be the product. What will be our nucleophile? So I think this is the only reaction so far we studied for the epoxide is the ring opening. So when you see the epoxide, if the reaction is the nucleophile attack the carbon and open the chain. And your nucleophile will be on one carbon and OH will be on the other carbon. So the only question is to identify the nucleophile, and then you will add on the nucleophile. For the anion nucleophile, it's easy, just attack on the carbon. For those nucleophile, you put on, obviously you will have this oxygen become positively charged. You have to deprotonate the H. So our nucleophile for this reaction nucleophile is CH3OH. Under this acidic condition, you will have this OH on this side, and that means your O and CH3 will attach on the other side. If you see the mechanism, you will see it makes sense. So sometimes you probably don't memorize clearly. Is the anion nucleophile attack one side, think about the mechanism. So if we take this previous example as the reaction for our mechanism, and we have this epoxide. With the acid, the electron can go from the oxygen from the epoxide, take the proton away from the acid, and this will be a very quick step. Okay, now this epoxide is protonated. Okay? So this oxygen is not neutral anymore. Right? It has a H plus on it. So next step, the nucleophile come in, attack, and this ring breaks. Okay? Now as what the study find out, this ring break. is a little more in advance. So that means the ring break a little more ahead. The ring break first. With the ring break first, you will produce some characteristic of the carbon cation. Okay. So again, I will probably first draw that, and you have this O. So this pattern become a break, and you still have the H. So after the OC bond in the epoxide beginning to already breaking some little bit, okay? And you will see the attack of the nucleophile. Because this is breaking first, so you will have some of the carbon cation characteristic on these two carbon. And then you have a choice which carbon you want to put the positive charge. Okay? If you put it here, and you have you kind of have a secondary carbon cation. If you put it here, you have a tertiary. So tertiary is more stable. In other words, you have more positive charge on this side, you have less on that side. And positive negative attract. So therefore this reaction will happen like this. This will be our slow step. Okay? So the first reaction is kind of an acid-base reaction. Okay? So that acid transfer a proton onto the other base. Now here you have to see those bond breaking bond formation to transfer H plus relatively easy. When you produce a carbon oxygen bond or break a carbon oxygen bond, that will be slow. Okay? So once you produce, you will see this become and you still have the H on the methanol. By the name, your step 3 will be the deprotonation. So what you need to deprotonate is that intermediate after you adding the nucleophile. After you add the nucleophile, you have this methanol is your nucleophile. Okay. Now methanol bonding to the carbon of that epoxide carbon, you did not lost the H yet. So right now your oxygen from the methanol have a 3 chemical bond. So you need to use some of the base to take the proton away from this protonated intermediate. So this reaction again, it will be faster reaction. Okay, now this is kind of review and the review. We talk about this in chapter 15, last chapter. Okay? Because of the nucleophile attack in step 2 from the last mechanism is SN2 reaction, that That means from the opposite side of the carbon-oxygen bond, epoxidation of the double bond and then hydrolysis of the derived epoxide is the method to prepare anti-Weissnier diols. So let's see, we have this cyclohexane. We first use peroxide acid, prepare the epoxide. Then the epoxide can be hydrolysis into the Weissnier, the so-called anti-diols. So what happens is you convert the double bond into the epoxide first. Now you have some of those stereochemistry, so this H here and this H here on the same side. In the last mechanism, we use methanol. Methanol and water are very similar. So they can be nucleophile, but not that good nucleophile. So the hydrolysis of the epoxide with acid as catalyst, and you produce the so-called anti-Weissnier diols. Right, you see the structure of this product, right? And you have two hydroxyl on the adjacent carbon, on one carbon and on the other carbon, another carbon. So you have two carbon have each carbon have a hydroxyl. We call them diol, right? So this is diol, and this is trans diol. Cyclohexane and cyclohexane diol. So as we know from chapter 15, there is another way to prepare the Weissnier diols. Similarly, starting with the double bond. But there we said we use double bond and we use osmium tetraoxide. And you produce osmate ester. And then you reduce that or oxidize that, depending on what you use. Sometimes we want to save the osmium because osmium is toxic and expensive. So what you do, you will produce cis 1, 2 those diols. So if we start with a similar reactant, it's cyclohexane. So this is also the cyclohexane. Last time you start with cyclohexane, peroxide acid, then hydrolysis, you produce the trans 1,2 cyclohexane diol. So you have the two hydroxyl is on the opposite side of your cyclohexane ring. Now this time, if you start with this, and you use some of those peroxic acid, one peroxic acid, peroxic acid, you can use peroxide. The peroxide and OS, O4. So this we say is our catalyst. This is catalyst. In some of the solvent is similar to this. Then you want to use base. Okay. So this is a peroxide. And then that's your product. That's your product. So this product is sort of CS1 to cyclohexane diol. Compared with other methods, from epoxide, and you will produce the trans. This is CS. Right, so we have OH, both are like a dash. Okay, now let me draw the trans. So this one is trans. The trans isomer of that. Right. So then the last section is about sulfide. First, how you prepare the sulfide. Sulfide is very similar as those ethers. Sulfide has a sulfur and a bond to two carbons. What you can produce to prepare the sulfide, you can start with those thiols. Thiol we study in the last chapter. And then you will add, for example, some of those base. Then you add some of those alkyl halide. And according to this equation, you can see you start with thiol like this CH3CO2 so this thiol is a little more stronger acid than those alcohol. So you can see this pKa is 10.5. Alcohol is about 16. Right? The thiol is a little stronger acid. So therefore, use hydroxide, it will be strong enough to totally kind of deprotonate or detonate away from the thiol, and you have this thiolate. Now this thiolate is a very good nucleophile. Right? So if you take some of the primary or secondary methyl or halide, this nucleophile, and do those SN2 reactions. And so SN2 reaction here, alkyl halide, methyl primary, secondary. But this base, this thiolate is not a very strong base. So if you have a very strong base, your secondary halide will eliminate reactions. So the secondary kind of in the middle. Either in the SN2 or the E2 depend on your nucleophile. So you replace, you kick out the halide out, you get this 2R. One R comes from your neutral thiol, the other R comes from your alkyl halide. Okay. Now one example is this. Okay. We have this alkyl halide. Actually is that vanillic halide chloride. And then we have this Thiolate, sodium thiolate, we already prepare take some thiol with NaOH. What they do is this for our SN2 reaction. I will not pay attention too much to the stereochemistry. So I will simply replace this guy, the Cl, by the S and CH3. Yeah, we did not study this stereochemistry too much because this carbon here, chiral. If you want to see those S and R configurations, so after this reaction, the configuration will totally change. And here we don't see those Y and dash, so we don't know what that R and S. If I show you this is the sum of those R or S, and then your product will be opposite. Just one reaction for the sulfide, oxidation. So the sulfide with the carbon, the sulfur with two of those bonds to the carbon, it can be oxidized depending on the strength of the oxidizing agent. You will have the sulfoxide, or you have the sulfone. So one example is this. If you take this methyl phenol sulfide, you use sodium periodate. Okay? It's a kind of oxidizing agent, but not that strong. And you put that in water, so that will become oxidized sulfur, and you still have this methyl. You are adding a double bond onto the sulfur. It's kind of analog to your ketone, but here it has sulfur. If you use a stronger oxidizing agent, and so we take this. Use, let's see, hydrogen peroxide, H2O2. Now this time, you add 2 arsen atoms. So that's about this chapter 16. Questions or comments? Okay, starting from 17, chapter 17, 18, 19, 20, so for the carbon mineral chemistry. this is all like how we use green yard with aldehyde or ketones, prepare those alcohols. So this is so that is like part of the carbonyl chemistry. And we'll start on chapter 17 today. First, the nomenclature. First, how to name aldehyde. Name aldehyde. The aldehyde functional group is carbonyl, and then at least one H. Carbonyl. So this is carbonyl. This is our carbonyl. A lot of compounds have the carbonyl. Aldehyde, it will have this. The other part, we call that R. The R can be C, okay? Can be R pure C, can be R pure C, okay? Or can be H. The name is relatively simple. Because this carbon that have the carbonyl are always the number one. What you do is just change your hydrocarbon to the alkane, the ANE, and drop the E and drop the E or replace the E by AL. Let's see a few examples. Okay, so this you choose the longest number of carbon, which is 5. Okay? And then you have 4, on the carbon 4 you have 2 methyl. Five carbon is pan. So pentane will be for 5 carbon alkane. Now you will drop the E. And then in unisize, you drop the E and replace by AL. So you have 4 dimethyl pentane there. The second example is this aldehyde and then this double bond. Aldehyde has a higher priority than double bond. So when you number the carbon, you're starting from the right side. Right, so we have a 6 carbon. So therefore, we have something hex. Okay. Because we have a double bond, so you don't have a hexene, you have a hexene. And you have to indicating where's the double bond. The double bond, because we number from starting from the right side, so therefore it's on the carbon 5. So our parent name is this hexene. Okay? And you will drop the E and change this into AL. Change the E into AL. Right. So when you have 2 in this example, you will name this benzene as a phenol. Okay? We have a 4-carbon chain. Okay, we have 4-carbon chain, okay? And the 4-carbon is built. For those diols, you don't drop the E because your name starting with a D. Okay? For the simple aldehyde, you have the Al. And you have the phenol. Then you have indicating where is the phenol. Because two aldehydes have the same priority, so which of your number doesn't matter. But you want to give the substituent the lower number. So therefore you starting from that side, 1, 2, 3, 4, and not from this side. Even though these two this aldehyde, they have the same priority, but because this substituent, we put like on the second carbon. There's a lot of common name, okay? So they become more used than the isotopic name. You're already familiar with this formaldehyde. If you go by what our system Al, so this will be our methanol. So next aldehyde is this. So the common name is acetaldehyde. Because you have 2 carbon, so the IUPAC name acetal. But acetaldehyde becomes so common, most people never use like the acetal or methanol. Another one, I think this one you saw on the exam today. So the common name is benzaldehyde. The IUPAC name should be benzene carbaldehyde. So that means if you have this the the carbonyl attached on some ring, you name this as carbaldehyde. Benzaldehyde is more commonly used than the benzene carbaldehyde. And let's see some of those examples we use the carbaldehyde. So if I have this cyclohexane, and then I attach this carbonyl on it, then the name will be the cyclopentene carbaldehyde. Cyclopentene carbaldehyde. So the pattern is you name this hydrocarbon as what you name as usual, and forget about this side chain. So just name this as a cyclopentane as usual. Right? Then add on this carb aldehyde or carbaldehyde. some of those aromatic compounds. Like naphthalene. Naphthalene have the number, it starts like on one ring. I think this will be our, size 0 will be our number 1, this number 2, 3, 4, 5, 6, 7, 8. You don't have a number that 2 in the middle, but that already have 4 chemical bonds. So what you see, this will be the 2. Naphthalene, run out of space. So that will finish the name for the naphthalene. You pretty much use the full name of your hydrocarbons. But just adding the carbohydrate. This is carbohydrate. Right, any questions?
What does that say before carbohydrate?
This one?
ENE or something?
Yeah, L, naphthalene, N-A-P-T-H-A-L-E-N-E.
Oh, it's all one word.
All one word, but I run out of space. You don't have to use dash. All one word. Okay, now there are some of those sort of precedents of functional groupers. The higher the oxidation state of the carbon bearing the functional grouper will give the precedence. So the carboxylic acid will have the highest priority. Okay? And sometimes you can remember this. Let's see some examples. If you have those functional grouper have alcohol, have aldehyde, and you have to know like what will have the higher priority. So let's see this have alcohol in it, and also have this aldehyde in it. You not name this something alcohol, right? You name this something as aldehyde. So aldehyde have a higher priority than alcohol, right? And you have 5 carbon. You want to name this as pentyl. You don't have to say 1 pentyl because this aldehyde always on carbon 1. Okay? Just have to locate or indicating where is your hydroxy. So this will be on the 5th carbon, so 5 hydroxy pentyl. Now if you have a cyclohexane, right? So now here you have this aldehyde is pointing down, hydroxy pointing up. So your name is stereochemistry because this is trans. This aldehyde takes a higher priority, therefore the numbers are starting from this side on the ring. 1, 2, 3, 4. Okay? So your hydroxyl is on the 4th carbon. 4 hydroxy. Then it will be cyclohexane, just everything is same as you name the cyclohexane. Cyclohexane. Okay. Again, I run out of space. You don't have to use space or dash to continue with that carbohydrate. name, you can name this as a benzene carboldehyde, but we will use our common name. Right? Obviously, if you just look at this part, you have phenol. Look at this part, you have that benzaldehyde. So benzaldehyde will have like a very higher priority because you have a higher oxidation state on the carbon. So the base name for this will be the benzaldehyde. You can use para or 4. Okay, so in this problem 17.1, you have 4 keratin, 4 like substance. And they have their common name. You want to put them into the IUPAC name. Okay, so the answer for the first one, you will have that you will have this base name of glucanol, right? But obviously you have that methyl, and your methyl is on the second carbon. So 2-methyl propanol. Okay, so this B you have a diol. If you have a diol, you don't drop the E or something. Just name that hydrocarbon 1, 2, 3, 4, 5. Right? So that's pentane. Just all one word. So for B, you have pentane diol. Right? For C, the aldehyde have the higher precedence. And you will see this become 2 and 3 dihydroxy and propanol. Now for D is very interesting. You can see there's a lot of those functional group on the benzene. You can name that as anosol by themselves. You can name that as a phenol. You can name that as benzaldehyde. Right? Benzaldehyde has higher priority. And when you will name that, you make a list of those substituents. Right? So you will have the 3. Don't write the name yet, I just make a list. 3 methoxy, okay, and 4 hydroxy. Then you put them in alphabetical order. Your parent name will be the benzaldehyde. So that was the parent name. Okay? And then you just make sure which one should go first, alphabetical order. H goes first. So write 4 hydroxy, 3 methoxy. So put together 4 hydroxy, 3 methoxy, benzaldehyde. Yeah.
Which one is this? Is this D?
This is D. C Similarly for ketone you have to use the number located where your carbonyl. So if I have a ketone like this, right, you can see this you have a 6 carbon, right? 6 carbon will be hexenone. Then you have to indicate the location of the carbonyl. And this is on number 3 carbon. You give the carbon as small number as possible. So this will be the 4-methyl and 2 pentanone. Now this one is some cyclohexenone. But you have this methyl here. And you name this is 4-methyl cyclohexane. Okay, so I basically we're adding ONE and N. Yeah, for this last one, your base name or your parent name will be this cyclohexanone. Okay? Then you indicate this methyl is on the 4th carbon. You don't have to see like this is cis trans. Because this guy here is flat. So it will not make this like on one side of the ring or the other side. Just imagine this just in the ring. Alright, so that's about naming those. There are a few more examples. You can also compare aldehyde and ketones. Aldehyde also rank the ketones. So if you have aldehyde ketone in the same structure, you will name the ketone as OXO. This one don't have that aldehyde ketones, but I think that's just one more clarity on this. Let's see, this one was named as 4-methyl 3 pentene, then 2 ONE. And on the next one, you will see that you have both aldehyde and ketone. Next one you see here. Right? So the last one I draw here, let me circle this. We have the ketone here, we have aldehyde here. Okay? So according to the table, the aldehyde have a higher precedence. Okay? So you name this as some aldehyde. And your number will start from this 1, 2, 3, 4, 5. Okay? So you will have let me write on the top. Okay? Pentanone. Then you can indicate those the ketone becomes substituent. And you will list them alphabetical order. Right? So the M will come first because methyl is for M. So you have 2 methyl. Okay? So these 2 methyl are on the 2nd carbon. Okay? That ketone becomes oxo. Okay? So then on the 4th carbon, 4 OXO. be named as a functional group name. Just identify that two alkyl or maybe aryl that attach to the carbon here. Let's see like 3 examples of functional group naming for the ketones. And then you will see your carbonyl is this part. So this is the carbonyl. Then you will identify what attached to your carbonyl. On the left side, you have that acyl. On the right side, you have the propyl. So you list this alphabetical order. You see this acyl, and then space, propyl, and adding the name ketone. So this is super the functional group name. You know the clearly indicating this ketone. The second example of the functional group name is this ketone here. So you have a benzylic or benzyl. And then you change the pen again. You just see your this part, the carbonyl. Then you identify what attached to the carbonyl. What attached to the carbonyl. On the left side, you have benzyl. On the right side, you have the acyl. And then adding the name ketone. Right, so the last one, you see the structure of carbonyl, then double bond, then double bond. So again, if you clearly indicating where the carbonyl, then you will see what attached to a carbonyl. Right? What attached to a carbonyl, the vinyl. Okay? So you have two are the same. And you see di-vinyl. Di-vinyl ketone. On this problem 17.2, you will do the opposite. Okay? So I'll give you those common names, and you write the structure first, then you put them into the IUPAC name. So the first one is so this, I'll give you those functional group name. Dibenzyl ketone. So you will have a ketone like that. Benzyl, so this will be one benzyl. Another benzyl. Okay, so this one. So you have two benzyl, right? You want to get the IUPAC name, not the functional group name, the substitutive IUPAC name. And you just name the carbon, 1, 2, and 3. Okay. So 3, that means you have propanol. Then on your first carbon and on your third carbon, you have that phenol. Propanol itself, you have to indicate where is your propanol. So this you have the 2 propanol. You do this. I think that obviously you're not going to put that in some other place. Then you will see this will be 1, 3. So B is acyl isopropyl ketone. You will first, if you use the functional group name, you first write this carbonyl group out. Okay. Acyl, so this is acyl, isopropyl, and this is isopropyl. Then you will label this guy from the, right now from the, let's see, from the number from the left side, but that will give you the methyl carbon number. Okay? So you will get this 1, 2, 3, 4, and 5. So you get two methyl and 3 pentanol. Right. Last cover we have methyl 2,2-dimethyl propyl ketone. Okay. So again this is the functional group name. Functional group name, that means you have to first, let's see, the ketone is OC. Acyl is easy, so that's acyl. So then the 2,2-dimethyl, let's say dimethyl propyl, so you have propyl like this. Then the sort of the 2,2-dimethyl propyl. If you take the propyl, that means your bond will bond to this part. So this is what our propyl. Now you have a 2,2-dimethyl propyl. So this is actually the new pentane. So that, then your bond or bonding to carbon is too long. So now let's name this with like the substitutive name. So this guy, our 2,2-dimethyl propyl. Well, you want to name this 1, 2, 3. You need to narrow this from the left side. You agree? So we need to narrow from the left side. So therefore we will have 1, 2, 3, 4, 5, 6. And it has 6, that means hexanon. And you have 3 hexanon. Now you are adding those substituents. Right? What is our substituent on this structure? Is 5, 5, 5, 5, 5, methyl, and dash, and that. Get a 1 there. And this one, this one, there is a 1. So let me change the name. So this is 1, 2, 3, 4, and 5. Yeah. No, that one for the other. Okay, so the last one is allyl methyl ketone. If you have the functional group name, you want to get the structure, you just see, let me put it here, it's easy. Allyl, so this is allyl, and then you have to attach this onto your carbonyl. So this will be our carbonyl here. Methyl, so that's methyl. So this is D, right? Now you want to name this, you have the number. Your number can only starting from the right side. Usually we have double bond on the left side, right? But so this ketone here takes the priority than the double bond. 1, 2, 3, 4, 5. So you will have a 2. You will have that 2. Well, how you name that? You probably one name to do that is 2 ONE, and then you will use the 4 indicating the double bond. Okay, so that's about how you name those structures. Any questions? Very briefly about the structure, then we'll do the quiz. The structure pretty much tell you have the carbonyl, in the aldehyde or the ketones. The carbonyl is current O bond, and your O is relatively negative. And you can see the resonance. So right now we have this structure, and if you follow the resonance, you have a double bond here, and O here, so 2 electrons here. Resonance, the electron like moving. So if I change the pen, and here, you will do this. Okay. So if you take one pair of electron away from the double bond, and you will get a positive charge on one carbon. Now we have a negative charge on the oxygen. So this carbon here, the plus charge now. And this one will be the minor contributor, and this one will be the major. If you want to move from the right to the left, you move the electron back. Now you have this carbon here. Even though in one resonance you will see clearly on the carbon that some of those positive charge. So therefore, this carbon will be the side that will attack by those nucleophiles. And this oxygen will be attacked by the electrophiles. So then you see this carbon here, use this kind of arrow, that means it's an attack. And this arrow here is also indicating what is attack this oxygen. One very good electrophile that will attack your oxygen on the carbonyl is a proton. Then compare the aldehyde with ketones. So aldehyde is relatively more reactive towards the nucleophiles than ketones. Because in like the aldehyde, you only have one H or one carbon. In the ketones, you will have 2 carbons, no H. And we know from the structure, so this part is relatively positive, and this part, the oxygen, is relatively negative. So the positive charge the carbon needs some of the electron to be sterilized. If some of the group of atom or atom bonding to that carbon has the meeting electron to it, then your carbon become sterilized. In terms of you have less positive charge, and then the nucleophiles will have less chance to attack. So this is about the beginning of this chapter 17. Chapter 17, 18, and 19, 20, as I said, is carbonyl chemistry. And a lot of times you will see the nucleophilic addition on the carbonyl carbon. And then in the next few chapters, you will see also some of those nucleophilic substitution. And then in chapter 20, you will see some of those electrophilic addition or substitution on your alpha carbon of the carbonyl. Those are it's kind of the enolated chemistry. Enolate is related to the carbonyl. All right. So I think this is about this. Well, I'm going to take like a little break, and then you are presenting your results for the quiz of chapter 15. So find your group members. When we talk about the quiz, I want everybody to pay attention to the other group of topic. Okay? I still see some people making a small little mistake.
That's what really
Number 4.
Presenting characteristic. Tomorrow you're presenting the characteristic.
No, we're doing 15. Yeah.
I know like 2 years ago. Oh, don't take it in the spring. Oh, yeah, it's been one of the other. Yeah, it's easy though. And they're out of the book. That card is wrong.
Oh, yeah, dude, I got it. Good. Yeah. Last time, 617. But that last Yates, like, I got it. Wait, it's more like I think it's a monster.
Tomorrow. Yeah. I mean, it starts out hard. The first half is really hard. And it's like. Another like that you go to. I don't know. CHP was too much. No, I took him in spring. Like, what? I told him. He was some Indian guy. I mean, I couldn't pronounce his name. Yeah. Really? Like the easiest, like I told you what was going to be on the you just study that. But I do not see it.
Number 4? Yeah, this is number 5.
A and B.
Yeah. Yeah, that was a question. Yeah. And you guys remember number 5, and I think number 6. You guys think number 5? 5. Number 6.
Every time.
Yeah, just write the. I think even at easy, it's like that class works, yeah. Like, spring is like spring for strong tissue. This is dark, plus with her. You just catch up on your other classes. Like every weekend I went out. Yeah, during spring semester, it's so chill. But then fall from New Year. Yeah, fall from New Year. You have like senior design. You have like mass transport. Yeah, you have like. Well, yeah, I mean, it kind of means like, again, most people are like smart as fuck. Dude, I know, I felt like, because everyone's like a kid who just like pay attention and get like straight A's. And like, you just awkwardly like, oh, shit, I'm getting. You don't want to say it because like, you're in class, like, you can break that back. Yeah, oh yeah, you're really into the math. I mean, I get no, for fall New Year, you use a lot of math. Yeah. But I mean, like, I don't know, I know everyone shares homework, so it's pretty solid. Yeah, I was doing pretty well. I actually understood it. I just messed up on the final project. Yeah, this one you're going to get. I chose a bad topic. That's what it is. Oh, the human being. I can't like too bad. Then you take, you gotta take physiology. I didn't like her. Both of them were 2 hours. One of them don't take because they were like, it was like a math lab class. It was like a math lab 420.
That's good, right?
It was like,
All by myself.
they were like graduate PhD students and they were struggling in class. They were like undergraduate. But then there gets another one. He has a bunch of classes where like all you do is read articles. So it's a lot of work, but it's like you need to. You can take anything for like that, right? Anything like engineering. Yeah, I feel like all shit happens to that. Are you doing culture? Yeah. I was thinking it's work. I mean, there's some kids that are so smart. They learn within 4 years. So it's like, oh shit. Like, are you doing BME or chemistry? You can say everyone does chemicals. No one does like BME. Oh, they got rid of BME. Oh, really? For me, you had a choice between BME, like graduate or semi-graduate. But like everyone just chose BME. Yeah.
So if you want the cake or the credit?
Yeah, I have him right now for research. I got to like every Friday.
You have trouble fixing it?
It's like mine is like tissue and
Yeah, I can remember that number.
so number 4.
You got 3.
So mine's like
Meeting?
yeah, I just emailed him. He's like, oh, I have like right now it's like from Brazil. They have some weird program where like government sign like and then like yeah, so there's a bunch of kids there, but like they all leave at the end of the summer. So he's gonna be like his last unit and
They have this detail on this.
he's pretty chill. I mean, mine is like anything that's
You can see like this. Those like the hydroid.
he just teaches you
Monohydroid
oh, just
or
finding something
hydroid.
online.
So this P or H is kind of H1 negative or T1 negative. So those are very good unifiers or
All the problems. I think everyone does it.
or H.
That's how you do it. That's the same
Everything at the P, right? So electron phase solution here, and these are the bonds.
I'm retarded.
Let it push it
I know, I
down.
was like media. It's like cold. So they got the grad and undergrad, and I can't even turn on my undergrad. I was like,
That becomes a
it's okay though.
O1 negative will probably some away from the That's possible on this because those guys already have so the iron layer. Down here, we can try to get the azo wave. Then you get the azo wave. That is very well.
Oh, yeah. I remember thinking that, but I was What is ALT for?
So I know all of them. We're not all fine. Plus I took like
and when you look at where we not all of them. You are saying that you want to hate you kind of
their own broth daylight. You can do like
why do you get one hand? All the four you are doing the four. That means that you want to run out of the video, all the four.
It was like right next to him. It's easy though. But that's gas station. It's like the most dangerous place in the world. Like, but there's a one kid like right next to him. This gets so many or something.
That's all I know. Oh, you never did that?
Yeah, it was like a newspaper, like school news, like a Facebook page.
Oh, this means this and that. And that's, even that is what gravity, like, that's gravity on the reason. So when you put on railroad,
But they're teaching shit. They don't think so. I want to be a public safety officer. I want to be an officer. Like, the chillest job. Like, I mean, I'm going to eat my house every day. I should have for a year.
the TV is those.
Like, I have so many friends who go like,
Very good, very good. There's some assholes. Finally,
my friend showed me a map they got, and it was like a map of the campus, and like a red dot was like it's in the whole
well,
campus.
here, you don't have this, OD. You have this. You don't want any hair with it. Center is the hair, you don't have a pH hole. You have a pH hole. What are the hair? Song is out, our candidates, you will. Alright, then we finish, you guys go to number 7. What do you do?
He gets it all.
So you mind to do also number 7? Number 7. Who wanted here to do number 8? I think who wants to do number 8?
If you do it, you kind of do it.
Oh, y'all do it. So 7 and 8.
Yeah, that's pretty solid. You probably
It's 12:30. Okay, so let's start. Let's start on this board.
You're on camera. I have like listen to some lectures.
Okay, so let's start from the
Like on like 5 minutes.
rightmost one. I want everyone like pay attention to what the professor is talking. Okay. So who did number 6? You guys?
We did 6 and 7.
6 and 7, yeah. Then go ahead and explain what's the problem, what is it. Okay. Would you like to go?
We go from here, do you want us to go?
Go to the
So number 6 is just an example of a Fisher esterification. So you have an alcohol and a carboxylic acid. You use an acid, it becomes an ester. So there's no mechanism yet, so that's basically what it is. For number 7, you have 2 different oxidations. One is fully oxidized, the primary alcohol is fully oxidized all the way to a carboxylic acid. And then you have the second one, because you're using a PCC instead of a formic acid, you're only going all the way to an aldehyde, not a carboxylic.
Very good. So this travel of the oxidizing agent, we have a few, right? PCC, PDC, chromic acid, potassium permanganate, and just make sure you know what oxidize what into what stage. All right, very good. So I think that's 2 is right. Any questions? So pay attention to see what we do, what the problem, even though you did it before, and that will give you increase your memory. Alright, now let's do the other one, that is number 4. Well, number 4, those kind of mechanism is number 4.
Alright, so this is the overall mechanism for this. So the first step is the ion transfer. It takes the hydrogen from HOSO to OH, and you can actually use H3O plus instead of that as well.
Yeah.
The second step is the nucleophilic attack. So you have the nucleophile attacking, and then the nucleophile attacking, and then you get water produced as well. And then the last step is the deprotonation, which you get from the OCH2 CH3 deprotonating the positive charge.
pathogens. Can you give the name? Yeah, I give the name for the second step. Okay, so exactly what is that is unimolecular or bimolecular?
It's fine.
Bimolecular SN2?
Yeah.
Yeah. SN2. 7-2? Yeah, SN2. The leading group in SN2 you always have like the nucleophile and the leading group in SN2. So what is the leading group in step 2?
It's still in right here.
Yep, the water. Okay, what? Number 8. Who did you did the number 8 to, right? Okay, number 8. Number 8, pay attention to the stereochemistry.
Oh,
Stereo.
It's
The C's.
So you have to draw the OHs at 6 on them. So either draw them both going away or both coming out of board.
Okay, so the mechanism is that osmonium is osmonium ion.
Osmium tetroxide.
I think the peroxide it attacks a double bond. It attaches 2 O's for that, and then then you go with the thing called carboxylic acid, and it breaks off at least
Yeah.
2 negative O's, which is protein. And that creates this.
And why the C's? As what the Evie said, the intermediate is called the osmium ester. So the osmium tetroxide, you have OS in the center, you have 4 oxygen. So the intermediate, you will see you still have the 4 oxygen on the osmium, and 2 of the 4 oxygen is bonding to like the 2 carbon from the same side. So that's the stereochemistry. Now the similar question is what we just talked about today. If you start with double bond alkene, and here you produce the cis diol, how can you produce a trans diol? So this is these 2 like hydroxyl like on the same side. And how can you produce that Washington 2 hydroxyl, one is up and one is down like this? Well, we briefly talk about today in today's lecture about what is today's chapter?
You can form an epoxide.
Very good, very good. You can form an epoxide ring. And how you produce an epoxide ring from the double bond?
You use like an MCPVA or a peroxy acid.
Yeah, the MCPVA is a peroxide acid. The metachlorine benzoic peroxide acid. Yeah. So that's all those patterns, right? There's another way to produce epoxide. There are only 2 ways to produce epoxide. Use the peroxide acid or the other way. You also start with double bond. You add the sort of the hydro. Halohydrin. If you add in VR, only VR, you are adding 2 Br on double bond. If you add Br2, if you add Br2 in water, so once the Br adding on one side, the water can attack on the other side. So once you have this, you can use some of those base, take the H away from the OH, then you will have the intramolecular SN2 produce the epoxide. Alright. So study, I think this chapter you already have the exam for chapter 15, right? And do the quiz before the class, we'll do the quiz like for tomorrow, chapter 16. Alright, any questions? Alright, we finished this part, right? Let's go on to that one. We'll start from the right. Put it to long right number 5, right?
Okay, so with 5A, we've got a diol right here, and this HiO4 is going to cut it right at the diol, opening up the ring, and it's going to take away your hydrogens and cause double bonds, and that's what we get over here. For part B, we have the bromine is going to leave when the sulfur, which disassociates from the Na, attacks, attaching the sulfur to the pseudopropyl. Okay? Does that make sense?
Allylic. Remember that one?
What?
That's allylic. And allyl, the position in allyl, right? Allyl bromide,
Okay.
allylic bromide.
Lily bromide. Okay. Questions?
Any questions? So next one, we did the one in the how the number 2, right? This is number 2.
Okay, we do number 2. We found out that water acts as an agent for Markovnikov addition. Is that correct?
If you have, but this one you don't have a difference, right?
Oh, yeah. So with H2SO4 as a solvent, it will add this OH in Markovnikov and have that alcohol coming off of it.
Yeah. If the double bond is not symmetrical, right? And then you will have that H adding on to the carbon with more H. Give me one example if you have to use the Markovnikov.
So,
Okay, so now you do the same writing and where you will put the OH. Let's go ahead of what you're seeing. Price is wrong. You can get that. You can get that. Use hydroboration oxidation, right? There you go. If you use the same reagent, H2SO4 water than mercury sulfate. You shall put that OH in the second one. Good. I think we should put more board in those, and then you don't have to sit there like 3 hours. We'll put more board on the
more
wall.
board,
And then,
Okay, we can write on the walls.
okay. Okay, you guys do the number 3.
Yeah. So this D, this attacks C, and I think, yeah, this jumps out, the electron jumps out from here to make the oxygen negative. So after that, so the D in this CH3O, because these both are like acids, but this one is stronger than the other one. So this attacks this oxygen and gets the D here. So it's like CO, E, and E here. Same with the second one too. Like the D attacks here, the carbon with the double bond, and electron jumps out of here, and then making oxygen negative. And then D2O is slowly burned up there, attacks this oxygen, and gives D there.
So pay attention to like those mechanisms. So next time we do on the exam, I will switch the NAD2, BD4 into NADH4. So now you will know what atom will attach to the property of carbon, right? Right. Any questions? Very good. Any questions?